So I welcome you all in this video. In this video, we will see a special type of DC-DC converter, that is the flyback converter. And flyback converter is again the step up, step down converter. So it is the advanced form of buck boost converter. First, we will see the circuit diagram of buck boost converter. Then how to do the modification to get the flyback converter from the buck boost converter, we will see. So this is the diagram of a buck boost converter. So this is the capacitor C, this is R, and across this R output voltage has to occur. This is D, this is L, and that is the MOSFET switch basically. Okay, and this is the input voltage. So here the output voltage is related with input voltage by this equation, D upon 1 minus T, where this T is the duty cycle. It is basically a T1 upon capital T. Okay. So, how to uh, draw the topology of flyback converter? So, what is the difference basically? Flyback converter, here the input and output are electrically isolated. Number one. Number two, here we are using the, instead of using one L, here we are using two magnetically coupled inductors. Okay, and otherwise you can say a high frequency transformer also. Means now I am going to uh, divide this L like this. So again, this is L1, this is L2, and this is the rest of the figure is same. So this is C and this is R. Okay, and this is R. Here V naught will appear. Okay, and this is the switch. This is the input voltage. Yes. Now we will see the orientation of this these coils over a magnetically uh, magnetic core, and since this switch is operating at very high frequency, so we can not use a simple core. Here we are using the ferrite core because it can work with the high frequency. But what is the orientation of these two coils? It is like if L1 is wound like this, okay, then L2 will wound as opposite to L1. Yes. So this is the orientation of coil 1 and this is the orientation of coil 2. Now what will happen? In this case, the orientation is same. So the diode is connected like this. But in the final figure, which is now I'm going to draw the final diagram of the flyback converter. So this is the that MOSFET switch, and this is your inductor L1. This is magnetically coupled with inductor L2, and the orientation is opposite, so that I have plotted like this, and this is the diode. Now here the diode is connected like this, and here the diode will connect like opposite to previous one. So one second. So here the diode will follow this sign, so it will connect like this, and this is the smoothing capacitor, and this is the load resistance R2 R, and across this R the V naught will appear. Now let us see the working of this flyback converter with the help of waveforms. So first of all, let us draw the switching cycle of the this MOSFET. So this is the on time, this is the off time, this is again on time, this is off time, this is on time, and this is off time. Okay. So this is the switching pattern. Now I'm going to plot the current, primary current. So when the switch is on, the current will increase gradually since L1 is there. So it will increase from some minimum value to maximum value. Let us say it is increasing like this. And when the switch is off, no connection between the input voltage and L1, so it will suddenly going to 0. then no current in the primary, then again it will increase like this. No current, then it will increase like this. Okay, so this is the pattern of primary current. Yes. In the Now let us see, there are two modes of operation. The mode one, when the switch is on, then let's say this is the that L1 I am drawing here, and this is the uh, orientation of winding. So when the switch is on, the voltage appears across this L1 is like this, and when the switch is off, mode 2, when the switch is off, then the voltage appears across L1 will change its sign, and in the L2, this is L2, since the voltage, it will just opposite to the polarity of the primary voltage, since the orientation is opposite. So this is the secondary voltage, and when the switch is off, the secondary voltage is like this. This is the secondary voltage. Now this secondary voltage, when the switch is off, is appears across this L2 like this. It will make this diode on, and the connection from the I mean this circuit will close, and the voltage across R will appear when the switch is off. And now this V naught is related to V in by this relation. So V naught is equal to V in. So D upon 1 minus D, up to here it is same as the buck-boost converter, but what is the modification? Ns upon Np. So this is the secondary and primary number of turns. And if we draw the secondary current, so secondary current will come into the picture when the switch is off. So this is the on, and this is the off, on, off, on, off. So when the switch is off, then uh, current will decrease from maximum value to minimum value some, then it is 0, then again current will decrease from maximum value to minimum value, then 0, then this is the pattern of the secondary current. If we plot the secondary voltage, if we plot the voltage across the coil L2, so you can see it is keep on reversing its polarity when the switch is on and off. So it appears like when the switch is on, it is negative. When the switch is off, it is positive. When the switch is on, it is negative. When the switch is off, it is positive. Yes. So this is the pattern of secondary voltage. And if we plot the voltage across the switch, then when the switch is on, so no voltage definitely, since it is a short circuit. And when the switch is off, so here you have to see, when the switch is off at this moment, so before this moment the current is having this maximum value, and after this moment the current is having this minimum value, means within the 0 second the current is changing its state from maximum to minimum. And this L is the voltage across any coil is basically L di by dt, and this is the voltage basically. So this di by dt means within the 0 time the current is changing. So that's why when we plot the voltage across switch, so it will having some peak here due to this action di by dt, because within 0 time current is approaching to minimum value. Then again it is when the switch is on, it is going to be 0, and when the switch is off, it is having some spike here, then again it is going to be 0. So this voltage is more than the input voltage, because it is having the input voltage plus the energy stored voltage due to the energy stored in the L1 when it was the on. Great. So this is the working of flyback converter. These are the waveforms. Now the what are the advantage? Advantage is that it provides the electrical isolation between the input voltage and output voltage. And second advantage is that it gives us the wide range of voltage control. We are having the duty cycle as well as secondary number of turns and primary number of turns. The job of this C is to consume the AC component from the output voltage, means it acts as a filter, as well as it will maintain the output voltage constant. And there are two modes of operation, continuous mode and discontinuous mode. So during the discontinuous mode of operation, the off time is pretty longer from the on time, so that inductor discharge earlier, and let's say inductor discharge at this stage. So this is the I mean dead zone when no current is there. That's why it is known as the discontinuous conduction. And sometimes in some textbook you can see the small inductor placed in series with diode, and its job is again to provide the filter circuit. This is the LC filter. Okay. Yes, so this is sufficient for this lecture, and we will meet in the another video. Thank you for watching this video.